Hello everyone. Today we are going to explain the research paper about the basic version of a state-of-the-art object detection technique named You Only Look Once, also known as YOLO. This presentation was made by me, Yash Kopulwar, and Dipanshu Gautam, whom you will be listening to after some time. So, have you ever tried spotting some real-life objects in clouds? I'm sure you must have. Isn't it awesome how we can recognize an object even by looking at its rough shape? When humans see something, they instantly know what the object is and where it is. And according to the industrial trend, we want this quality too in machine. The early detection systems were based on simple classification, that is, whether the image contains object A or the object B. Later, we were able to detect the location of the object by sliding different sized window over the image. But all these methods could detect only one object in one image. And these methods also checked a single image multiple number of times. Few techniques like RCNN was able to overcome these issues and also detected multiple objects in a single image. But these were computationally very expensive. YOLO, on the other hand, is a clever convolutional neural network for doing object detection in real time. I mean, the previous methods were also clever, but not real time. The algorithm only looks once at the image in the sense that it requires only one forward propagation pass through the neural network to make predictions. Let's look into the details. First, we will see how to detect a single object with only one single forward propagation pass. Our objective here is to predict class of the object and make a bounding box around that object. Let's consider a vector y as a label to this image. In this vector, PC is the probability for the object. That is, if the object is present in the image, value of PC will be 1. If the object is not present in the image, value of PC will be 0. Bx and by are the coordinates of center of the bounding box. Bh and Bw are height and width of the bounding box respectively. C1, C2, C3 are the class probabilities. That is, if the object present in the image belongs to class C2, value of C2 will be 1 and the value of C1 and C3 will be 0. To prevent the explosion of the numerical values, we will keep the measurement in the image from 0 to 1. That is, the origin will be at 0 to 0, 0, 0 and the other end will be at 1, 1. Now with the images and the labels available, we can train this model with a simple convolutional neural network. The job of this model is to predict if an object is there in the image, the location of the bounding box, and the class of the object. We will save this trained model for future use. Well, the method till now was already used in other object detection techniques. Now we will see the most interesting part of the YOLO algorithm. So in YOLO, the image is divided into several grid cells. Each grid cell is passed through the pre-trained model explained earlier as a single image. The predicted vector is almost similar to our y vector. Here, PC tells whether the coordinates of the center of the bounding box of the actual image of the actual object, even I got confused. Or else we can simply say that if the center of the object is present in the grid cell, the value will be 1 or else 0. Rest of the variables are same as vector y. If we take example of this image, it has 9 grid cells. There will be only one vector for each cell. Therefore, the dimension of the label for this image will be 3 cross 3 cross 8, where 8 is number of variables in the vector y. Now I hand over the presentation to Dipanshu for further explanations.
Thank you, Yash. Yash has already given you the overview of the algorithm, that how it works. Now let's try to analyze it more deeply and how the paper actually implements it. So as a first step, let's say we divide the image in S cross S grid, and each grid cell predicts B bounding boxes and confidence scores for those boxes. So now here confidence scores is PC, that as you can see in the right side of the figure, a vector you can see. So here PC is the confidence scores, and how it is calculated? It is calculated as a product of the probability of object and intersection over union. Intersection over union, it is also the main key point of the paper that they have used. So they have taken the intersection over union of the predicted box and the ground truth box. So basically what they are trying to do, they are trying to take those bounding boxes only which are having the maximum overlapping with the ground truth box, and this they are calculating with the help of intersection over union. Now each bounding box consists of 5 predictions as we have discussed earlier as well: bx, by, bw and bh, and a confidence pc. Well, these 5 predictions are fixed and the rest element depends on the number of classes. So if we consider 3 classes are there, then there will be C1, C2, C3 as well. So each grid cell also predicts C conditional class probabilities, probability of class I given object. These probabilities are conditioned on the grid cell containing an object. So now the predictions can be encoded as an S cross B cross 5 plus C tensor. And now this will be more clear in the coming slides at how the dimension of this tensor came. Now one of the key points to note is that this algorithm predicts one set of class probabilities per grid cell. So each grid cell can predict only one object, regardless of the number of boxes B. So if the object size is small and there are multiple small size objects in the image, then we should divide the image into more number of grid cells, say 19 cross 19. That might help to some extent. So in the paper it is mentioned that for evaluating YOLO on Pascal VOC dataset, the value of S is equal to 7 is taken and B is equal to 2 is taken. The Pascal VOC has 20 labeled classes, so C would be 20. And the final prediction would be 7 cross 30 tensor. And the formula that we have given in the earlier slide, in the previous slide, that is using S into B into 5 plus C. So basically S is equal to 7 here, so 7 cross and B is equal to 2 here. So 2 5s are 10 plus the number of classes, which is 20, that is 30. So that's how the dimension of the final output tensor came. And now let's have a look at the network design of the algorithm. So basically we have a convolutional neural network, and the network is inspired by the Google Net model for the image classification. It contains 24 convolutional layers followed by 2 fully connected layers. So basically the last layer, as you can see, that is a layer of dimension 7 cross 30. So as we have divided our image in the 7 cross 7, so basically we had 49 grid cells, and in the output you can observe that there are 49 vectors of dimension 30. So basically for each grid cell we are predicting a vector. Now the vector is of dimension 30 because we are predicting 2 bounding boxes per grid cell. As we have seen earlier, we are predicting 2 bounding boxes per grid cell. So I hope this clarifies that how the dimension of the output vector came. And now let's move forward. So we have seen that there are 49 grid cells in the image, and each grid cell is predicting 2 bounding boxes. So there are a total of 98 bounding boxes that the algorithm is predicting. But we don't want all these bounding boxes. We just want the relevant bounding boxes which are actually enclosing the object. So if we have 2 objects, we would want that the algorithm should predict 2 bounding boxes. So now how to avoid these extra bounding boxes? So to avoid these extra bounding boxes, what they have done is that they have used the first of all, they have used the intersection over union and non-maximum suppression. So first of all, they have set some threshold based on the value of intersection over union between the predicted box and the ground truth box, and they have set some threshold, let's say 0.6. So those boxes, those bounding boxes, those predicted bounding boxes which are having the IOU value greater than 0.6, we are keeping those and we are removing others. And finally, they are using the non-maximum suppression. So basically the bounding boxes which are having the higher probability, we are keeping those only. So it helps us to remove the extra bounding boxes and keeps only the relevant one. So now as we have gone through the architectural design of the algorithm as well, let's have a look at how exactly the training happens. So first of all, the convolutional layers. So we have used a convolutional neural network, and the convolutional layers first of all are pre-trained on the ImageNet 1000 class competition dataset. So basically they are using the pre-trained convolutional layers, and then they are training their network for approximately a week, achieving a single crop top 5 accuracy of 88% on the ImageNet 2012 validation set, comparable to the Google Net models and the Cafe's model zoo. Now, just to note that for the final layer, they have used the linear activation function, and for all other layers, they have used the leaky rectified linear activation. And output is optimized with some squared error, but it does not maximize the average precision, it seems. So therefore, the loss function was changed a little bit. That we would be seeing in the next slide. That what is the exact loss function they are using. Now let's have a look at the loss function that they have used in the paper. Now here you can see 5 terms are there, and you can observe 2 constants are there as well, lambda chord and lambda no object. So let's first understand that how they have considered the loss. So they have divided the loss into 2 parts. The one loss is the localization loss, basically the bounding box loss. That how much the predicted bounding box is differing from the ground truth bounding box. And the next is the classification loss. But here there is a problem. We cannot weight localization error equally with the classification error. That might not be the ideal, because in every image, grid cells do not contain any object. This pushes the confidence scores of those cells towards 0, often overpowering the gradient from cells that do contain objects. This can lead to the model instability, and it can cause the training to diverge early on. Now to remedy this, they have used the 2 parameters, lambda chord and lambda no object. They have taken the value of lambda chord is equal to 5 and lambda no object is equals to 0.5. That is, they have increased the loss from the bounding box coordinate predictions, and they have decreased the loss from the confidence predictions for boxes that don't contain objects. So here in the first term, that is the first term is the error considering the center of the bounding box, and the second term is the error considering the width and height of the bounding box. Now one more thing is here. We have taken the square root of the width and height instead of taking width and height directly. So this to avoid the thing that some squared error equally weights errors in large boxes and small boxes, but that is not the case actually. The error matrix should reflect that small deviations in large boxes matter less than in small boxes. So to partially address this, they have taken the square root of the bounding box's width and height instead of the width and height directly. So I hope the first 2 terms, the first 2 loss terms are clear, and the last 3 terms is for the classification loss. And in the last term, you can observe that they are considering the loss over the whole classes basically. So that's how the loss function is they have used. Now let's have a look at some comparisons of the YOLO algorithm with other methods as well. So as you can see that YOLO algorithm is quite fast, at the same time having high accuracy. For example, YOLO has a mean average precision 63.4 with a frame per second of 45, and fast YOLO has 155 frames per second with a 52.7 mean average precision. Other methods are able to achieve the good accuracy, but they are not actually the runtime is not really good. Now some limitations of YOLO. So as I have already said in the previous slide as well, that each grid cell detects only one object. Now if each grid cell can detect only one object, so if there are smaller objects and if there might be 2 objects in the grid cell, then it cannot detect. It can detect only one object. So that is one of the limitation of the YOLO. It struggles to generalize objects in different configurations or orientations. And the model uses rough features to a large number of downsampling layers. So we have already seen that there are 24 layers in the network. Basically 24 convolution layers along with the 2 fully connected layers. So basically that is they are using the rough features. And same error values have same weightage in large and small bounding boxes. They have basically they tried to avoid it partially, but it's still that is they have used some trick. They have used a trick that I have discussed earlier. or that is they have taken the square root of the width and height of the bounding boxes in the loss function. And the last one is I would like to say that is to classify smaller objects, image needs to be divided into finer grid cells again. So you might divide into 19 cross 19 or even more. So with this, I would like to end my presentation here. Thank you for being the patient listeners.